Thank you all for coming. This is the last talk of the fall term. I want to thank a couple people who have helped make this happen over the last couple weeks, last 2 months. First of all the grad students who were involved in making sure that this food could be here each time. We really appreciate that. All of those who attend, students, faculty, folks from the USGS, who consistently here, we appreciate that. The CBO, Jogami, and also interested public, thank you for coming. Also, make sure you check it out next term. Adam Booth is going to be organizing things. There's going to be some really interesting talks, so stay tuned for that. Lastly, just mention if you're taking this for credit, 407, 507, make sure you sign in on the sheet. Okay, this is the last time you have to do that for this class. Yeah.
If this is the last lecture of the course, can we also?
You can personally take the bag and you just all. So yeah, we have some more food that may be coming in at some point here. We'll keep our eyes out. Is actually the food outside? Yeah. Around the corner. Okay, fantastic. So I just want to mention the food that's around the corner here in honor of our guests. We have jelly sandwiches and creme brulee, I believe. Thank you to Mary Eichhorn for making that happen. We appreciate it. Yeah, so we'll let the speaker decide which one he prefers, and we'll see which snack he chooses. Figure that out. So without further ado, our speaker today, last of the term, is Peter Molnar. He's an all-around expert on mountain building, including both the creation of mountains and the collapse, in some cases, or destruction of mountains. He's also looked at the interface between climate and tectonics in the past. So he attended Oberlin College. He got a BA from there in physics in 1965. He was co-captain of the lacrosse team. There he completed his graduate studies at Columbia University, 1970, where he got a PhD in seismology. Interestingly, he was a National Academy of Sciences exchange scientist with the USSR for 4 months. That was in the 70s. He joined the faculty at MIT in 1974. And then in 2001, joined the faculty at the University of Colorado Boulder, where he's currently half-time professor. So with that, let's welcome Peter Molnar to Portland State University.
Thanks, John. I hope I can control this. Sorry, back up. Some of you take this for credit. This talk has a fairly long introduction, and then the first 2/3 are really based on a paper that Philip England, Craig Jones, and I wrote just earlier this year. I'll get to the last third when I get to it. I didn't put this in the title of the talk, Dynamic Topography, because if I had put it in the title, then I would have written disparaging words, as you will see. But this is what this talk is about, and the basic idea of dynamic topography with variance is you have flow beneath the lithosphere. Here's the lithosphere. Upward flow will lift the surface. Some downward flow will deflect the surface. And this topography is dynamic in some sense because the flow is a key part of it. Now, you'll see I'll be a bit more hostile in a little bit. This is a concept that, this is a pair of words that have been used with increasing frequency. Philip England compiled this. This is a plot, 1995 to 2005. The number of times the words dynamic topography are used in papers, if you plot it in a logarithmic way, exponential growth with a doubling time of roughly 4 years. This is a really popular idea. My great hope is that this will plunge back down and we won't have to worry about it too much longer. Okay, here's a summary of 5 maps of the Earth. In all cases, Africa is centered in the middle. In all cases, the red shows regions that are high relative to some average, and the blue regions that are low. 5 different versions. The paper in question here, Flamand, Gurnis, and Mueller, and then 4 other papers. And you might say, well, they look pretty similar. It's pretty much red in the Pacific in all cases. It's pretty much red over Africa, though different amounts, and it's blue when you get over Eastern Asia. So you might say they look similar, but let me point out that they differ by 1,000 meters. If you compare these, they're all calling for topography of order 1,200 meters in studio dynamics, but they differ by 1,000 meters. Now I've got a bargain for those of you who think that this is not important, that these are all alike. Similarity here, I got a bargain. These are similar. They all have a president in the picture in the middle and numbers on the side. And those of you see me afterwards, I'll give you 100 of these for just one of those. It's a bargain. I might even up it a little bit if you're really eager to make a deal. But I contend that 1,000 meters is a big difference. Okay, back to basics. Isostasy, Archimedes' principle applied to here. This comes in two variants, and of course, any combination of the two. Airy, back in 1854, 1855, said that you could have, where you have high terrain, the crust would be thickened, the crust is less dense than the mantle. This is like an iceberg floating, ice cube floating in water. This is one variant on this idea. So high terrain is underlain by thickened crust. The other variant, Pratt, who did the work that laid the groundwork for Airy, then watched Airy explain it. I was quite upset, and a few years later he had a different version. And that is that the density would vary laterally across the region. The easiest way to make it vary laterally is to have it vary the temperature. So hot in the middle, cold on the outside. But a high area then would be underlain by less dense material, in this case, drawn now with 20% terminology, with a hot mantle underneath. As I say, you can have combinations of these. And there's some depth of compensation, where below that depth, the pressure or the weight of the rock above is the same everywhere. There's a key assumption when you assume this, when you make that, treat everything as isostatic, and that is you've ignored vertical stresses on, shear stresses on vertical planes, vertical shear. That's often overlooked, but that's a key. And these area isostasy works pretty well in places like Tibet, Altiplano, in the Andes, high mountain ranges like that. Pratt isostasy accounts for the depth of the ocean floor, huge variation from 2.5 kilometers to 6 kilometers, difference in depth, difference in distance to the center of the earth, and high regions like East Africa Basin Range, and I'm going to argue as well for the Southern Rockies. So let's go to the, I think, Southern Rockies, or the Rocky Mountains of Colorado. This area, this is a shaded relief map. Of course, you're getting low out of here, coming up the Great Plains, going into the Rockies. This area is high. And as I'll show you in a second, there are those who think that this is dynamic topography. Okay, this is a plot, and she and her colleagues 20 years ago plotted along this axis is the average elevation, going from 0.5 kilometer to 3 kilometers or so. And this is crustal thickness. And if area isostasy worked, if crustal thickness varied with height, high areas here would have thick crust, low areas thin crust. You fall on one of these lines. Where these lines are I switched from a Mac, so some of these numbers disappeared, but there are some of these symbols. But these these lines describe the density contrast at the MOHO. Well, you can see the data don't fit any of those lines. It's straight across, and I think few would doubt area isostasy simply fails, just plain wrong. When one looks at gravity anomalies, so this is topography on the left, high, getting up to 3,000 meters in here. Isostatic residual gravity anomalies, these are the gravity anomalies you would predict if you were in isostatic equilibrium. Numbers are here on the order of tens of milligals. As you'll see, those are small numbers, I would argue. That's what you'd have. So the region is in isostatic equilibrium. You have some kind of compensation. And going back again, roughly 20 years ago, Leningrad, the average shear wave velocity in the upper 200 kilometers is about 9% greater beneath Kansas than beneath the Rockies. 9% is a very large number. This is not small. Most of tomography works in the 1% range. It doesn't work in anything. This is huge. And the conclusion, the logical conclusion, hot mantle beneath the Rockies implies the mantle density is low. The high topography is at least partially due to buoyant mantle. So Pratt isostasy, what else? Has to be Pratt isostasy. That's where we were 20 years ago. We've now spent the better part of $750 million on EarthScope and things like that, so we have much better data. And it's now dynamic topography. Title of the paper, Mantle-Driven Dynamic Topography. This is a profile through using all this modern seismology, going from the Colorado Plateau in the west, out to the Great Basin, Great Plains, going through the Rockies. Warm colors show low P wave speeds, low by 1 to even 3%, big number. Contours in here are for S wave speeds, 4.1 kilometers per second. Here's a very low S wave speed in the upper mantle. Well, I suggest I want to offer you a concept in the perspective of how things have gone from 20 years ago, what we understood to what we have now. A car is parked on a hill, and who or what drives it? Well, you'll all agree, gravity drives it. Gravity pulls it down, right? But it isn't going anywhere. So somebody else has to drive it. Could be the brakes, could be the driver slipping the clutch, could be a big stone behind the tires. Probably only a small number of you have had this experience, but it's possible that something else is involved. I can assure you this has happened. Anyway, that's my view of dynamic topography applied to the Rockies. They just sit there. I don't know if you ever heard the old joke when you drive up to Maine and you get a little bit lost and you ask the Mainer sitting on the front porch in his wheelchair, "Excuse me, sir, but where does that road go?" And he looks at you and he says, "Don't go nowhere. Stay right where it is." That's the story with the Rockies. They're not going anywhere. Mantle-driven dynamic uplift of the Rockies as a concept is what drives. Sorry, it's like what drives parked cars. Okay, so we need a definition. One of the great mantle dynamicists of the 19th century, Dumpty, said, "When I use a word, it means just what I choose it to mean, neither more nor less." He made this statement shortly before he took a great fall. We will move on to more modern definitions here. So what does dynamic topography mean? It's supported by convectively maintained stresses generated by the viscous flow throughout the mantle and buoyancy variations within the lithosphere. Very precise definition by Lieutenant Forte. In this context, this would be dynamic topography, that would be dynamic topography. But this is the mid-ocean ridge, the cooling of the seafloor, 2.5 kilometers here, 6 kilometers depth down here. This would be dynamic topography by their definition. They're quite explicit about it. This is what they mean. I'm pleased that they are explicit, but most of us would say we haven't learned anything about why this is shallow here and deep there from the study of mantle dynamics. This has been known for 40 some years from plate tectonics. It's simply cooling of the lithosphere, but it's their definition. Another definition, supported by vertical stresses at the base of the lithosphere that are generated by flow in the mantle. It's got rectal and silver. So this is this part of it, but definitely not that part. So this is basal tractions, but not isostatic compensation. This is basal tractions plus isostatic compensation. Now, one more. This is topography originating from sources beneath the upper thermal boundary layer of mantle convection. Not a very precise definition. Apparently, it means basal tractions, pushing or pulling the lithosphere up and down, but not isostatic equilibrium. But in short, this is what you get out of a model. Okay. I have a bit of philosophy interspersed through this talk. Dan McKinsey was one of the two people who gave us plate tectonics, gave us rigid plates. Trouble most people in this business is they think because they got a bigger, faster computer, they can make more complicated models that are more realistic. They should realize that they cannot, because they cannot solve the equations, and they're stuck having to use the big machine. They must make the model simpler if they want to understand the results. Science is aimed at understanding. So that's enough about models for a while. Okay, that's all been the introduction. Now I want to consider one example, possible example of dynamic topography. Map of southern Africa. This area, roughly 2,000 kilometers across, of order 1,000 meters high, quite high. and as I'll show you, is often asserted to be a good example of dynamic topography. The logic behind this is because of the seismic wave speed distribution at depth in the Earth. So this is near the core mantle boundary. This is greater depth, Africa in the middle. Warm colors are showing you low speeds. Low speeds commonly are thought to mean low density. So low speed material, low density material will be rising, be pushing Africa up. Then cross sections, east-west cross sections in here. This is Africa. Low speed material down here, presumably rising, and cross sections with different orientations. Now, as I said, a number of people have asserted that there's dynamic topography in Africa. Forte had the courage to say no, it's zero. Forte and his colleagues. But here's a bunch of other numbers. Now, you might say, well, John et al., they say 300 meters. These guys say 360, so they're really not different. That's not very different. This guy, this pair say 650. Well, they don't differ by very much, so they're all the same. And they get up to 700, and that's so they get the same. And maybe that's a little bigger than ours, but you might say these really aren't very different from one another. But come on, they can't all be right. You can't say 1,200 meters and 300 meters are the same when this is the ball game you're talking about. And those of you who think they can all be right, let me just remind you for after this session that I have this bargain that I'm offering them if you think that they could be right. Okay, how can we look at this? I'm going to borrow first a classic problem from Stokes. Stokes considered the situation if you have a sphere, it's more or less dense than a surrounding fluid. If it's more dense, it will sink through that surrounding fluid, or in the reference frame of that fluid, the fluid will move around it. The rate that it moves past the fluid goes as the square of the radius times the density difference times gravity. Put it on Jupiter and go faster. Inversely with viscosity. So to make it low viscosity, it'll go faster. This is a classic formula. It's one of them. It's used in volcanology, sedimentology. It's used in Mantle Dynamics. It's really one of our fundamental ideas. Jason Morgan, the other, we had McKinsey. Jason Morgan was the other person who gave us plate tectonics. He took this and said, well, what happens when we put a roof on the top, or more precisely, we take away a half space above, so we have no material. So we have a sphere down here. Let the density be, let it be less dense than the surrounding material. So the density difference is delta rho, negative number. It's like it rises. When it rises, of course, it's going to push the surface up. This is dynamics. He calculated the speed at which it rises. This is Stokes, and then this is an approximation that goes with it. E is the ratio of the radius of the fluid to the depth of the fluid. So obviously, as you get shallower and shallower, E gets bigger and bigger, and this term becomes bigger and bigger, and the sphere has to slow down as it gets near the surface. Now, Morgan solved the whole problem, all the fluid flow within the surrounding material. So you can solve all that, so you can get the normal stress at the surface. Normal stress consists of a pressure due to the flow plus a dB toric stress, where again we're defining the terms as over here. This is an approximation. In fact, I've kept one more term that Morgan didn't keep, but the terms that are ignored get small except for spheres that are very shallow. Now you can then say, well, if you've got a normal stress here, that will be balanced by the weight of the rock. So the density of the rock that you lift times gravity times the height, that's going to balance the normal stress. And I put an M here because if you're lifting a large area, you're lifting the mantle, you're not lifting just the crust. You're lifting the moho is going up with you. And hence you can basically invert that way and put that in, and you get an expression for the height. Now, and this again is an approximation because of terms, but don't worry about that. Okay, interesting fact, the height is independent of the viscosity. I'm not going to dwell on that. Morgan, of course, saw that. It's independent of gravity, I might point out also. Leave that for those of you who want to ponder something in case you get bored with something else. Now, gravity anomalies offer a test. Gravity anomalies, the deviations of the gravity, the rate at which a particle accelerates towards the center of the Earth, allow us to make a test. There are two mass anomalies that contribute to our gravity field. First of all, there's the sphere, less dense, of course, so it's giving us a negative gravity. It's And that's simply Newton's law, Newton's constant of gravitation, times the mass deficit of, or mass excess of that sphere, divided by the distance squared, but then we measure gravity perpendicular to the surface of the Earth, so we have a correction in here. We wind up with something like that. And we have a second term from the topography. And you'll notice this is written so that this all looks the same. 4 pi a cubed over 3a is the diameter of the sphere, density, big G, with all that stuff. So we can calculate what gravity would be if we had a sphere like that, a sphere at depth with a certain density difference. Well, we can turn this around and say, well, all right, we're going to put a sphere at some depth, certain size, but we want to make it so the height is 1,000 meters. South Africa is 1,000 meters high. So this is an example of 4 situations, 2 different depths of spheres, 1,000 and 2,000 kilometers, and 2 different radii. So 500 kilometer radius, 1,000 kilometer depth is the narrow, is the red one. These 2 are both at 2,000 kilometer depth. In one case, 500 kilometer radius, the other 1,000 kilometers. And then we can calculate the gravity anomalies. And the gravity anomalies look like this. Along the axis down here is distance from the center where that sphere is. And these numbers, this is all linear, so if you wanted to make this 1,200 meters high, you increase these by 20%. It's just a linear problem. Okay, well, let's make it simpler. Let's just look directly over the sphere. If we do that, and we consider the case of 2,000 kilometer depth and 100 and 500 kilometer radius, we get 1,000 meters high. Remember, that the sphere gives you negative minus 46 milligauss. The surface deformation, you get plus 138. So the difference between them gives you 92 milligauss is what you should see. And if this were a decent enough model for Africa, and I would argue it's plenty decent enough, despite all the simplification, you'd predict 92 milligauss free air gravity anomalies or isostatic gravity anomalies over Africa. Well, I have to digress a minute. Oh no, yeah. So these are the predictions. So no topography, no gravity anomaly, 1,200 meters. It's bigger than what I showed you before, more like 110 milligauss, and then everything in between in there. Okay, gravity anomalies. I want to work with isostatic gravity anomalies. Let me just digress for a second here. If you have topography that comes up in the air, that's a gravitational attraction. That's the correction that you make. Well, that's not correction. That's what you get from that topography, that green line. If it's compensated by a crustal root, so less dense crust than mantle underneath, reaching down so that the mass in the column is the same both under and outside, the root gives you this blue line, which is a bit more spread out because it's deeper than the green line. This is the Bouguer anomaly, by the way. And then if you combine these, you take the difference between these essentially, you get the free air gravity anomaly, which looks like this. So the free air gravity has some not noise, but some complications. The isostatic anomaly, of course, would be 0 because everything is constant. So I'm going to show you the isostatic anomaly. I'll come back to free air anomalies a little bit to discuss that. But that's the isostatic anomaly over Africa. Here's a scale, plus or minus 10 milligauss. You get these little blotches here and there. 10 milligauss. So this is what other people from their dynamic topography claim. As I said, Forte says 0. Well, 10 is pretty close to 0. 28 milligauss, 28, 25, and so forth. Seems to me that those calling for gravity anomalies bigger than about 10 milligauss fail. So what we do when they fail is we just get rid of them. And this is what we're left with. There's essentially no dynamic topography in southern Africa. That's a summary statement. One has to, you don't want to be too strong in your words, so it's a little more than zilch, and you have to find zilch where you're down here. It's 100 meters. Okay, let's come back to this. As I said, if you have these edges, you get gravity anomalies near the edges. So the next figure is a global map of free air gravity anomalies around the world. And you can see some positive anomalies around Africa down here, near the continental margin. Well, if you go back, if you go, that's the free air. If you go to the isostatic, they go away, right? If we go back to free air, they're there. Big free air anomalies along in the Andes, but of course a huge contrast in crustal thickness along the Andes. So if you look at the isostatic anomaly, pretty nearly gone. Go back up in here, you have a pair of anomalies in here. This is the Himalaya. You have flexure, flex the basin down, so there's a deficit of mass. You're supporting part of the mountains in here. So these are definitely deviations from isostasy. We've known about this for more than 30 years. When you look at the free air anomaly, it's a much bigger signal because of this edge effect. You're going from thick crust here to thin crust all around. So the point is that the free air anomaly is not the one you want to work with. You want to work with the isostatic anomaly, although, as some of you may know, there are problems with it. When you look at the isostatic gravity anomalies, they're pretty small. There are places where you have big values, almost surely due to lower mantle, masses in the lower mantle. In that case, up in here, almost surely because Pleistocene rebound of glaciers up in here hasn't been completed, so the surface is still depressed, probably lower mantle. If you put a long wavelength filter on this, of course, you can get rid of all those things, and you're back to essentially nothing under most of these. So free air gravity, isostatic gravity anomalies are less than about 30 milligauss everywhere. This is a bound. And if dynamic processes are supporting topography that's out of isostatic equilibrium, they're not supporting much because that number is small. And we can put another number on that. The simple formula, the gravity anomaly is 2 pi times Newton's gravitational constant times the density of the material that's been lifted or pulled down times its thickness. And in units that are easy, 41.9 milligauss per gram per cc per kilometer times the density contrasting gram per cc times the thickness. So you can do what geophysicists do all the time. You can invert this, if I may use that word, the height anomaly that you would get with a gravity anomaly if it's due to some layer of density rho that's been lifted or pulled down is simply this ratio, which is 30 milligauss per 41.9 milligauss per whatever, times the density. I put a mantle density in here because if you're lifting a large area, that's 0.2 of a kilometer or 217 meters. That's all you get. It's really not very much. Dynamic topography is mostly isostasy, and only a small part is really due to the stresses that are involved. Okay, now let me take another perspective. Going back to this paper, it's one of the first ones that I showed you in this fourth slide, I think. And they dynamic topography is that topography due to flow, tra-la-la, tra-la-la. It's dynamic because mass anomalies driving the density are moving. Get your lawyer to translate that, I'm not sure what that means. But, and then this contrasts with isostatic topography, in which the mass anomalies are in a state of quasi-equilibrium. I want to focus on one word in this statement, this word right here, contrasts. What quantitatively is this contrast? And pay attention because I'm going to give you a quiz, a few slides. And you're expected to give an answer. Okay, I'm going to consider dynamic topography in its simplest form. This is, to my knowledge, the simplest example it's ever been used. Again, by Dan McKenzie, right? You have a half space. You don't worry about one dimension, y coordinate goes out forever. You put a temperature distribution that's harmonically variable, sinusoidal function on the top, a wave number k. Let the heat diffuse into the solid underneath. So you diffuse heat in where it's warm, diffuse heat in, it gets warmer where it's cold, you diffuse heat out, it's cooler. I don't think any of you should be surprised by that. Now, we make a couple of key assumptions. Assume the viscosity is large enough that this temperature distribution can be sustained. So there's going to be slow movement of this fluid underneath, but so slow that the temperature structure doesn't change. Because of coefficient of thermal expansion, and you have differences in temperature, you'll have differences in density. If you have differences in density, you have a body force, forces of flow, and you can solve for that flow. You can calculate the flow, stream function, velocity, stresses, the whole flow by making this assumption and knowing this temperature distribution, which decreases exponentially with depth going down. Z is increases, but decreases going down. And an astounding result, you're all going to be really amazed at this, where it's hot, material rises, where it's cold, over here it sinks. I realize you're just shaking your head. But this is really what you get when you do the mathematics. Hot material rises over your things. And you get flow. And you can calculate everything. You can calculate the dynamic topography. In fact, you can break it down into two parts to the dynamic topography. Part due to the pressure, because the pressure in the fluid varies laterally, and part due to the normal deviatoric stress, which turns out to be smaller. Okay, that's what you get. What would you get if it's an isostatic equilibrium? What would the topography be if you had isostatic equilibrium? This is quiz time. Would the topography in isostatic equilibrium be larger than, smaller than, or equal to the dynamic topography? How many think it's larger? 1. How many think it's equal? How many of you think, oh, sorry. 1, 2, 3, 4, 5, 6. The rest of you are thinking, right? Yeah. So the rest of you will say the dynamic topography is lower. Is that right? You'll say, good. This is a trick question, but the trouble with this trick question is, you know how a trick question works. You figure out what the answer should be, and you guess the opposite, and you're right. But I've given you 2 possible opposites, so it's a trick question. It's a good way to do it. I'd like to start by saying 2 of the smartest geodynamicists I know in the world have gotten this wrong. So some of you are should feel at home with brilliant people. The isostatic one is higher. It stands higher, and it's very simple. Why? When you have isostasy, you don't have stresses, shear stresses on vertical planes. When you have flow, the shear stresses on vertical planes resist the flow, so they keep the topography from being as big as it would be otherwise. So we have dynamic topography, very popular term, growing in number of papers, doubling every 4 years. But dynamic stresses don't enhance topography, they limit the topography. So we can ask the question, dynamic topography or dynamically inhibited topography? Another reason why I hope the term will go away. Or be replaced by this. This would be better. Okay, so that's the first 2/3. The last third is the hardest part of this. This is work done with Greg Hausman, 2 studies that were published in the last couple of years. And I want to look at mountain ranges because that's how I first got into this. Dynamic topography of mountain belts. How does Mantle Dynamics help build mountain belts? If it does. That's kind of a clue, though it's a deceptive clue. Okay, a little bit more philosophy. Philip England, one of my dear colleagues, usually they start with one thing they don't understand. Here, that's the key, right? We're trying to understand here. Then they make a model with a large number of parameters that are included in order to make the model realistic. You can guess where this is going. But then they're unable to investigate parameter space fully, and they wind up with 2 things they don't understand: the Earth and the model. This is not progress. This is going the wrong way, right? I mean, we're trying to understand, and we start with, you get the picture. So what we've done, Greg Hausman and I in this case, is consider a very simple situation, which sadly isn't as simple as would be best. Rayleigh-Taylor instability. This is the instability that develops when you have a dense layer over a less dense layer, so it's intrinsically unstable. So think of a lithosphere over an asthenosphere. But the lithosphere in this case has a crust, which is buoyant on top, a mantle portion of the lithosphere, which is slightly more dense than the asthenosphere, so it's unstable, though you have this buoyant layer on top. And the asthenosphere, to make it simple, we're going to make it inviscid. It's such low viscosity, it doesn't matter. And then what we do is we perturb the shape of the bottom. We put a perturbation so the instability will grow, make it a little thicker here. When that happens, that will go down, make it a little thinner over here, and it will go up because we draw material down. And look at that. Well, there are 5 numbers that govern the solution. There's a dimension. Do this all in dimensional space because it simplifies everything. There's a dimensionless wave number. A wave number is 2 pi divided by the wavelength. So if we non-dimensionalize the thickness of the layer, we have a dimensionless wavelength, wave number or wavelength, where the thickness of the sphere is the scaling dimension here. We have a ratio of viscosities, a crustal divided by a mantle viscosity. There are only 2 viscosities in the problem, because we've assumed that this one down here is 0. We have a ratio of thicknesses, thickness of the crust to the total thickness of the layer. We have a third thickness, but it's not independent, so we have only 1. But we have 3 densities, so we have 2 independent density contrasts. So, a bit more philosophy. This is a quote. Fermi, that Freeman Dyson took. He heard Fermi say this. I remember my friend Johnny von Neumann. Johnny von Neumann was one of the great applied mathematicians of the middle of the last century. Used to say, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. We have 5 parameters. We are not Johnny von Neumann. We are not Enrico Fermi. We are not Freeman Dyson. We don't make our lithosphere wiggle its trunk by any means. But we can make this a bit simpler because some of these numbers we know well. We know the densities pretty well. We know crust is thinner than it's less than half the thickness of the whole lithosphere. The big numbers that really matter are the wave number or wavelength of the perturbation and the ratio of viscosities of the crust to the mantle lithosphere. So suppose that number, this is this ratio, crustal viscosity to mantle lithosphere viscosity. Supposing it's big, really, really viscous crust on top. If you perturb the mantle lithosphere so you have sinking in this area, rising here, sinking, rising, and so forth, you pull the moho down, crust gets deeper, but this top layer will just be pulled down with it. Its viscosity will keep it following what's going down underneath. So you'll have subsidence where you have sinking. If you have a viscosity ratio that's near 1, this turns out to be the best for making thicker crust. Where you have material sinking, pulls the moho down, but it draws crust into this, fills this up, and pushes the surface up. And conversely, where you have thinning of mantle lithosphere, so this is rising, the moho goes up when you have divergence of material away. So you actually thin the crust up. And then if you have very low viscosity crust, here, like water, then you hardly have any topography because you can't support any stress. You have a little bit of positive topography, but not very much. So you have that pattern. Well, the scientific question that we're asking is, because we're not going to play with most of the free parameters, what, if any, viscosity ratios the sinking of thickened mantle, of cold mantle lithosphere contribute to the building of mountain ranges? Clearly, this doesn't contribute. It goes the wrong way. We're pulling the surface down. You're not making a mountain range by sinking material here. You are, in this case, not making much of it. So I'm going to show you a bunch of calculations. First, just to give you a feel for what numbers we're talking about. Most mountain ranges are in this range, 150 to 300 kilometers in lateral dimension. So the wavelength would be 300, 600, twice that. Mountain ranges are just the crests of the sinusoid. Wave number, remember, 2 pi divided by wavelength. We non-dimensionalize by multiplying by thickness, the spheric thickness of the order of 100 to 150 kilometers. So the dimensionless wave numbers we're talking about are in this range 1 to 3. I'm telling you this because the next sequence of figures, we want to focus in that range. Because everything, again, is done non-dimensionally. Okay, just taking this one case where the crust is much more viscous than the mantle lithosphere, where you're pulling the surface down. This is the case, the dynamic case, where you pull this down, sinking as a function of wave number. We're mostly in this 1 to 3 wave number range in here. The dashed line, in fact, is the case for isostasy. So once again, same result as we got from the case that McKinsey considered. The isostatic one gives you bigger topography. You had this column in isostatic equilibrium with the thickening mantle lithosphere. You pull this down more than you do when you have the dynamic case, where the stresses are then resisting the flow. This isn't important for mantle belts. I put it in for mountain belts. I put it in just to say that the case I gave you before was not a rare situation. It's quite plausible. Okay, this is now a range of values of this ratio of viscosities from very low crustal viscosity to crustal viscosity 10 times bigger than mantle lithosphere. And the ideal case, the ones with the biggest topography, in the one wave number range 1 to 3, is this viscosity ratio around 1. That's the case when the solid lines are the case with calculated with the dynamics. When you allow isostasy, you get lower ranges. In this case, don't think that this is an exception to what we had before. This is consistent with what we had before, but it's a different picture from what you get. Now, this doesn't help us very much. Much better is to go back to gravity anomalies. Gravity anomalies is something we measure all around the world. We can use them, and they have been used for decades in the study of mountain building and other processes. This is a plot now. Everything's dimensionless again. You want to think in this 1 to 3 range. And I haven't put in the case of the big, very, very viscous crust because it's not relevant to mountains. And the gravity anomalies are negative. Calculated gravity anomalies in all cases are negative, or maybe small, but still negative for that viscosity ratio. The dashed line is what you get for area isostasy. They're all positive in this case. So dynamic stresses create negative gravity anomalies for nearly all relevant wave numbers and viscosity ratio. The dashed lines with area isostasy applied. Okay, the best way to look at this then requires I go another step further and look at what's called the admittance concept that was introduced back 40-some years ago by Dorman and Lewis, but really brought forward by Dan McKinsey again. This is a ratio of Fourier transform of the gravity field to the Fourier transform of the topography. So it's a function of wave number. You might say, well, it should be complex. These are complex numbers. This should be complex. It turns out that it becomes complex only in the wave number range. It's not interesting. So for a simple case, suppose you have topography harmonically varying with a wave number K0. The gravity anomaly looks the same as the scaling factor in front. The admittance is the ratio of these. Of course, the Fourier transform of that function is just a delta function with K0. So is that, they cancel. So you wind up back with the same 2.5 kg times density we had before. If you have isostasy, remember with isostasy you have a compensating layer at depth. And that introduces another factor, this factor in here, e to the minus K0 times Z0. Z0 is the depth of compensation. This is the same topography, but now with this compensating depth. So the admittance has the same form as this, but it's 1 minus this exponential. This exponential, you can see when you've got a very, very large K0, a short wavelength, you don't see the compensation depth. This is a big number e to a minus big number of 0. This goes down here, back here. If you have a very deep compensation depth, same thing. Your surface, you have surface doing this, and you have a perturbation in density way down there. You don't see that. It just goes away. So you get a form that looks like this. This is classic, well-known, basic geophysics. Okay, so what do we get with our calculations? This is now the admittance, non-dimensional. If you want to make it, put it into milligauss per kilometer, you multiply by that number. It is pretty nearly 0 or negative in the key range. Now this is now plotted log base 10 of the dimensions wave number. So if the dimensions wave number is 1, the log is 0, so you're here. If this is 3, the log is about 0.5. So the important part is this range right here. And the dimensions impedance, admittance is negative or near 0 for all of these in the range that would be pertinent to mountain belts. The dashed line is area isostasy. That's a positive number. It goes up to this big number up here because you're getting to very short wavelengths compared to the compensation depth. So you're getting a number that's big. Remember that 2.5 G times density. Whereas out here, where you have very long wavelengths, low wave numbers, everything cancels, so you have nothing. Okay, what does the real world look like? bunch of studies, different parts, different mountain belts around the world. Observed admittance is always positive. So each of these, this is wave number going out that way. If you want to convert it, if you have a 100-kilometer thick lithosphere and you want to make it dimensionless, multiply by 100. And so you're really in this range of 1 to 3 in what we're talking about. You can convert it to wavelength up in here because all of this has been done in dimensional space. The key is they're all positive. So this makes the logic of drawing a conclusion very simple. Calculated admittances are negative. Observed admittances are positive. Dynamic contribution from flow-induced normal stresses topography is negligibly small. It's going the wrong way. If you want to make it big, it's going to make this worse. So it's just not important at all in the building of mountain ranges. This doesn't mean that dynamics aren't important. It means that the stresses due to the flow, pressure due to the flow, are not important. They change densities. That matters. But in isostatic equilibrium. So I'm just about, so this is kind of a summary slide. I have a few more slides. My simple view of things, you have crust, mantle lithosphere, mountain belt, you shorten, plate motion, convection moves mass anomalies to thicken crust, moving plates are thickening crust, you get thick crust, but you get thick mantle lithosphere. That's unstable, that's heavy, and that wants to go away. So that goes away. It's light blue up here because it's gone, but it's showing you where it used to be. That sinks and goes away, surface comes up. So Mantle Dynamics moves mass anomalies around to thicken crust. It removes mantle lithosphere. You get a buoyant response to that going up. But all that happens in a state nearly isostatic equilibrium, nearly meaning a couple hundred meters. Those of you who work in Tibet, 5,000 meters, you don't care about 200 meters. You will if you have to walk up it, but you're not going to care about it in your interpretations, I don't. So I'm going to leave you with a mnemonic for how you might remember what I've said. Ask the question, what distinguishes a good auto mechanic, distinguishes good ones from bad auto mechanics? The key is mechanics. You want people who understand mechanics, right? And if you really want the ultimate in a mechanic who understands mechanics, the ultimate would be his or her understanding of Einstein's theory of relativity. I mean, that, you can't beat that. So the analogy is simple. I would argue that isostatic compensated topography is to Newtonian mechanics what dynamic topography is to relativistic mechanics. Most of geology, geophysics, atmospheric science, the whole works, doesn't really need to know relativist mechanics. A little bit does, so we can't throw it away. Most of what we do down here, and I would argue most of you don't need to care about dynamic topography. So to leave you with this, if you're content with an auto mechanic who does not understand Einstein's theory of relativity, why should you care about dynamic topography? And I'll leave you with something more interesting to look at. Thank you.
Thank you, Peter. We have time for questions if anybody has any.
Yeah.
Well, can a good case be made for dynamic topography at spreading center?
Well, this is
Because those are submarine mountains, essentially. Right?
yes, but this is the way Mucha and Forte look at it. They call it that way, but I would argue that we understood why the mid-ocean ridge has shallow water, has topography at only 2.5 kilometers depth, and why it got deeper. We've understood that for what, almost 50 years, for more than 45 years. We've understood that. Dynamic topography, the words came in 1985, 30 years ago. None of what we've learned about mantle dynamics has helped us to understand that. So you can include it as Mucha and Forte do, but they're not bringing us forward with understanding. They're just defining something that way and making it fit their definition. Most people don't use that definition. None of the other people I quoted include that in their definition of dynamic topography, including Dumpy. He doesn't have that in his definition as well, though he could, because he defines it however he wants to.
What would you say in the case of like a plume, and where there's been like geologic evidence, like where you can measure the deformation of, say, like the ocean seafloor around Hawaii, and you can measure that swell. What would be a good term to call it at that point? Because you can.
I'll answer everything up to that last question. Yes, you have 1,000 meters of topography. The seafloor is 1,000 meters shallower over surrounding Hawaii, over a dimension of 2,000 kilometers horizontally. So 1,000 meters over 2,000 kilometers. It's shallow, no question about it. The gravity anomaly over that is of order 30 milligauss. 30 milligauss. If that were completely pushed up by stresses at the bottom, 1 kilometer, you're underwater, so you don't get the big gravity anomaly. You get a gravity anomaly of the order of 90 milligauss, not 30, but 90. So I would argue that a third of it, roughly a third, 300 meters, something like that, is supported by dynamic pressure and deviatoric stresses. But most of it, 2/3, is just isostatic compensation of a hot region underneath. Now you can put words in there, I mean, definitions and all that, but my goal isn't to define anything. My goal is to understand, and I think gravity allows you to understand the contributions of those two separate parts.
Just a quick follow-up. What about in a continental setting, say like where you had, say, the interior seaway during the Cretaceous, like where it's been proposed that subsidence was driven by processes not associated with.
It's easy to wave your arms on these things. Those calculations, of course, what they do is they take present day plate motion and they run it backwards, and then run it back forwards again, and so forth. But if you want to put time in mantle flow, you've got to have a parameter that has time in it. Well, gravity has time in it, but you're not going to say you don't know gravity. Viscosity is the parameter that has time in it, which you have to do to scale everything. When you non-dimensionalize your equations, well, actually, you usually use thermal diffusivity in convection, but for these sorts of problems, again, we know that's not going to change. It's viscosity you have to know. So if you want to go back to Cretaceous time, 65 million years ago, if your ignorance of viscosity is a factor of 2, and if you think you know viscosity within a factor of 2 just about anywhere in the Earth, let's talk about this bargain I'm offering you. I'll give you 250 of those. And, this is crazy. But as soon as you say there's a factor of 2 uncertainty in viscosity, then 60 million years ago, you can't tell 30 million from 60 or 120 million. They're all the same. So you can run your calculations, but you're turning more knobs than you have any control over. You can say it, but we're nowhere near being able to show that that's what made the interior seaway. And the interior seaway is partly there because in Cretaceous time you had a smaller volume of ocean basin.
I have a question in terms of removal of mantle lithosphere. You talked about that a little bit here, how that predicts an increase in surface topography. So do you see that there is in your mind, is there the possibility of subsidence prior to the uplift that's dynamic?
Yes, and there are people looking at that. There are people claiming they can see it. But yes, you'd imagine that if you bring this blob of material together, the surface would come down and then this would break away. The drift would come free and the surface would lob back up. And this is a target for tectonic structure and sedimentology people. And there are people claiming they can see it.
You would think you would see it somewhere.
Well, there are claims in the Andes. There are claims that people see it. I don't feel qualified to evaluate the work. They're very small. They're not the regions where these are claimed are they're not Hawaii-sized features. These are small features. So whether they are seeing this or not, I remain agnostic on that. But yes, I would think you might be able to see.
And would you call that substance, that initial subsidence, dynamic?
Yeah, I might. Well, yeah, no, there's some. I mean, what Morgan did is beautiful stuff. Oh yeah, Max and I, we had to learn Einstein's theory of relativity too, you know. We don't use it. He does. Somebody, yeah.
Speaking of viscosity and time, for your models, are you viewing the crustal lithosphere as a Maxwellian solid, as a viscoelastic solid? And my question, my question really is that crustal response of an eta prime of 1, will that eventually look like the crustal response of an eta prime of 0.0? Will there be a relaxation associated with that?
No, this is ultra simple. This is Newtonian viscosity, no elasticity at all in this. We did allow for this to have an elastic layer above it, so you could deform, and that of course acts as a filter on shorter wavelengths. So in one of those two papers we included that, but it's a strictly linear viscosity. It's a very poor approximation of Earth materials, but you have to start somewhere, and so this is the first simplification, and how it evolves we don't know. We're looking at an instantaneous solution. We're not looking at any finite entropy.
The second to last slide of the first half of your talk, I think, was the simple convection solution and lots of dynamic topography as well as the isostatic topography. Are you assuming there that basically the entire mantle is isostatically compensated by the outer core? That's how the calculation is done?
Yes. I have slides in there, yes. We cheat, right? Yes. But that's why I leave the other one in that is with the large viscosity contrast, because it gives you the same answer. And so Max's point is that we cheat by saying we have isostatic compensation going to infinite depth. You don't have to go that far down. You have to go down, well, it's of order 1 wavelength, and you're already the isostatic part is enough. But for that one, yes, it's integrated all the way down. And you probably know that the kernels, Parsons and Daly and Hager and Richards, those kernels, if you look at those kernels, they will tell you always will get the result that we're getting because of the nature of the kernels. And I took that out as well. That takes too long to go through.
So what kind of vertical velocities are required in the mantle to support this dynamic?
That's a good question. I think most of them are in that high, that 100 millimeter a year range. I don't do any of that. I didn't even, thinking about Morgan, I didn't even think about what speed his viscous sphere would be rising. I didn't make, I could. The formulas are all there, but I didn't even think about it. But that's generally the thought. I think in that 100 millimeter. They're not Kimberlite speeds. They're not outrageous speeds. They're typical light motion speeds, I think.
So you think it's a lot lower than that? Just
sorry, no. This is the fluid speeds underneath. The surface is going up much more slowly.
Yeah.
That's if we could measure rates that surface was going up, we could do much better. We could get at viscosity, because for the reason that the viscosity drops out of Morgan's problem, it reappears for the same reason if you can measure the rate of change of vertical motion. Well, there's almost no place you can do that. Those rates are far too low. Still far too low for even GPS. They're sub-millimeter.
There's another class that's going to be coming in here in just a minute. So let's thank Peter for coming one more time.